Hi everyone. In this video, I'm going to talk about two things I learned recently about LLM Foundry while working on a group research project. Two things are, number one, LLM Foundry by default, when using a Hugging Face Llama model, does not use the efficient flash attention varlen func and instead uses the flash attention func. In other words, it doesn't unpad the batch by default, and we'll look at why. And then two, when you do force LLM Foundry to use flash attention varlen func, it slows down training time. So this video, I'm going to kind of walk through my entire process, including how we figured out these things and how we eventually got it to work, and then the surprising result that it slowed down training time. For those of you who are new, my name is Vishal. I'm a data analyst transitioning into machine learning, and this is the channel where I'm documenting my journey. So first, let's quickly talk about what is flash attention varlen func and what is flash attention func. So these are two interfaces, flash attention interfaces that are provided by the flash attention library. And based on what your input data is to the attention mechanism and to the flash attention interface, it performs calculations differently, but it gets the same result. So when you use flash attention varlen func, what basically happens, like if you could imagine that you have a batch, let's say you have 4 items in the batch, and each item in the batch has a mix of padding and non-padding tokens. So flash attention func, which is the kind of regular padded batch interface, will take the batch with padding tokens and it'll calculate the flash attention or the attention computation on that batch. And so you're kind of wasting the quadratic compute on a bunch of padding tokens that are not giving you any information. So that's flash attention func. And again, I'm not an expert on flash attention. I'm definitely learning more as I go along. So in a couple more months, I'll have a better explanation of what's going on. Flash attention varlen func, as the name suggests, allows variable length sequences. And so what it receives as expects as an input is not a batch with 4 items with padding tokens. It expects a single item with no padding tokens, but with boundaries established for the different sequences. So let's go back to our batch of 4 items. We strip the batch of padding tokens, and then we concatenate all the non-padding token sequences together. So we have a single item instead of 4 items in the batch. And then we also have another tensor where we say, okay, the first sequence, the first batch item is from, let's say, 0 to 200. The second one is from 200 to 400, so on and so forth. And so what you're doing is now you're stripping the padding tokens from the input. And so you're performing the attention calculation on fewer tokens. And so in theory, it should go faster. So that's a quick, a little bit hand-wavy explanation of that. So the core functionality of which flash attention interface is used is dependent in part on the value of the attention mask. And we'll look at that in a second. So the model that we're using is small LM2 135 million, and it uses the now deprecated Flash Attention 2 module. I think it was deprecated in October of 2024. And the first time in the Llama model, so this is the highest level module, in that forward pass, the first instance where attention mask is used is in this update causal mask method, which takes attention mask and a bunch of other items. So if we look at update causal mask, and this is happening, if we go here, here's the Llama model. Let's zoom in a bit. Here's the Llama model. And here's the forward pass. And here's the update causal mask. So what update causal mask does is if you're using Flash Attention 2, which we are, and if the attention mask is not none, and if there are zeros in the attention mask, then it returns the attention mask. Otherwise, it returns none. So my understanding of this is that if there are padding tokens accounted for in the attention mask, then it returns the attention mask. If the attention mask is all ones, then it returns none. Why is this important? Why are we so focused on the attention mask and its value. So we'll come back to this attention mask being none or not none. We'll come back to that later. But this is all tied into when flash attention varlen func is called in the Hugging Face implementation. So for now, let's assume 0.0 is an attention mask. So the attention mask is kept in the llama forward pass, and it's passed on to the decoder layer, and then it's passed on to the attention mechanism. Inside the attention mechanism, Hugging Face uses the underscore flash attention forward method. And that method is defined in the modeling flash attention utils.py file in transformers. And in here, there's two conditions where flash attention varlen func is called. One condition is if attention mask is not none. That's the key condition that we're going to be concerned about, which is why we're so concerned about what is the attention mask value. And then the second condition is if position IDs is not none and max length q is not none, query length is not equal to 1, and this torch diff is not always greater than 0. And we'll talk about that in a second. So this position IDs condition is going to be true if position IDs is not none. If query states.shape equals 1 is true, then that's the second kind of subcondition that is to be passed. If max length q is not none, or if this thing right here. So torch.diff basically looks at consecutive items in the tensor, and it takes the difference between those consecutive items. And if those differences are not greater than or equal to 0, then this would be false, and not false is true. And that is not very intuitive, so let's look at an actual example. So let's say position IDs was something like this: 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 0, 1, 2. What that means is we have 3 different sequences concatenated together, so packed together. So this is where the concept of sequence packing comes in. And the first sequence is 0, 1, 2, 3, has 4 tokens. The second sequence has 6 tokens. The third sequence has 3 tokens. So if we looked at torch diff, the difference between 0 and 1 is 1, 1 and 2 is 1, 2 and 3 is 1, 3 and 0 is -3. So is that greater than or equal to 0? No, it's not. So that would be false. So basically what this not torch diff condition is basically saying is, do you have multiple sequences packed together, and do your position IDs reflect the starting points with 0 for each of those packed sequences? That condition is not coming into play in this exploration, so I'm not going to go into it in more detail. So the condition that I'm concerned about here is this one. If attention mask is not none, it'll call upad input, so it'll unpad the input, and then it'll pass those outputs from unpad input into flash attention varlen func. So it has these query key value, this cumulative sequence length, which is important, which we'll talk about, and then some other items. So if attention mask is not none, flash attention varlen func is called. That's why I'm so concerned about what are the conditions where attention mask is none, what are the conditions where attention mask is not none. All right, so how do we check the value of attention mask during training? Because ultimately we're trying to figure out which flash attention interface is being used, and then we're trying to make sure that the flash attention varlen func is being used, and then we're going to inspect the training results based on that. So to inspect the value of attention mask through different points in the model, because if you recall here, the high-level llama model does receive the attention mask, but if it doesn't have any zeros, causal mask, after going through update causal mask, is going to be none. And then down here, the decoder layer will receive as attention mask a causal mask of none. So if my attention mask has all 1s, causal mask is none, attention mask is none, flash attention varlen func doesn't get called. If my attention mask has 0s, causal mask is that attention mask, and that gets passed through the decoder layer. Attention mask is not none, flash attention varlen func gets called. So let's inspect the attention mask value at different points in the model. It tells a clear story when you look at the attention mask in the overall model forward pass, the decoder layer forward pass, and then the attention mechanism forward pass. So to do that inspection, I wrote a composer callback, and writing composer callbacks is one of my favorite things to do because it just is so cool to me that you can plug in you can kind of inject in all this logic and inspect what's going on inside of the composer training loop. So I'm going to do this before forward, and what I'm going to do before the forward pass gets called is I want to print the config attention implementation just to make sure it's flash attention 2. And then I'm going to write this closure, this like function factory where I pass a name and then it defines a hook function using that name, and then it returns a hook function. I then use register forward hook to attach the hook to the attention layer, to the decoder layer, and to the model as well. And the hook handle I'm going to pass to this self.hooks list, append to the self.hooks list, so that after forward I can remove the hooks and it'll continue without you having those hooks in there. So what is my hook function doing? Well, first it's checking if attention mask is in the keyword arguments, and then it's saying, okay, for this module, so attention layer, decoder layer, or model, is attention mask none? And then it's printing out, attention mask is none. So if it's none, this is going to be true. If it's not none, this will be false. If attention mask is not none, then I want to inspect some values about it. I want to look at the attention mask itself so I can kind of visually inspect it. I want to see, is 0 in the attention mask? I want to look at its shape, and then I want to look at its sum, because the sum will tell me if there are zeros in there. It's another way to check that there are zeros in there, because, for example, the shape is 1 by 2048 if I have a batch size of 1 and a sequence length of 2048. And if the sum is less than 2048, then that means that there were not just ones in the attention mask, there were zeros as well. And that's it for my hook. Because I'm using keyword arguments, or I'm inspecting keyword arguments, register forward hook, you have to pass with keyword args equals true. And that's it. That's my callback. So LLM Foundry pre-training by default does not have an attention mask with zeros. It has an attention mask of all ones. And that's what I learned from inspecting the output. So attention implementation is flash attention 2. Attention mask is none in the attention layer. That's true. So my attention mask never gets passed to the attention layer by default for pre-training in LLM Foundry for a Hugging Face model. The decoder layer also doesn't see an attention mask because it's none. If we look at the model, attention mask is not none because the model does receive the attention mask, but it doesn't contain any zeros. And as we can see here, it's all ones. The shape is 2048 in the sequence length dimension, and the sum is 2048. So what we're basically seeing is that there are no zeros. So if we go back up here to this update causal mask, it's not none, but it doesn't have any zeros in attention mask. So it's not going to return the attention mask, it's going to return none. So this basically lets me know that the reason LLM Foundry, by default, using its pre-training collator, doesn't end up using Hugging Face's Flash Attention varlen func implementation is because the attention layer never sees the attention mask. And the reason it never sees the attention mask is because it does not contain zeros. And so the model's forward layer passes none as the attention mask. So the next question is, okay, that makes sense, but how do we now create an attention mask with zeros? So if you look at LLM Foundry data textdata.py, this is where the default pre-training collator is defined. It's called concatenated sequence collator wrapper. And inside the call function, or dunder call method, we can see that it creates the batch, and then it adds a sequence ID, and then it returns the batch. So I used cursor, which was the first time for me, and I added this simple line to that dunderCall method where I defined the attention mask as the output of batch input IDs is not equal to 0, and then returning that from Boolean to numbers. And so what does this mean? When input IDs are not 0, then attention mask will be 1. So these are the kind of non-padding tokens. And when input IDs are 0, which is the EOS token ID that small LM2 135 million uses, the attention mask will be 0 because this will be false, and false as a number is 0. So this is a kind of nifty way of converting my input IDs where I have non-zero, non-padding tokens. So these are the actual, tokens that are corresponding to the words in my sequence. Those are not 0, so the attention mask is 1. And because I'm using small LM2 135 million, the EOS token ID is used for padding, and the EOS token ID is 0. And so that's going to be a value of 0 in the attention mask. So this is one way to kind of force LLM Foundry to have zeros in the attention mask. One side point is because I'm using modal, and in the way that we are doing modal is that we have this Docker file, and it brings down the repo with LLM Foundry and installs that and sets up the environment. And so textdata.py already exists in the LLM Foundry repo that gets cloned down to the modal image. And so what I have to do is that I have textdata.py locally where I have this modified collator. And then I do image.add local file. So I take my local file and I'm saying, hey, copy it, basically overwrite the existing textdata.py. And it overrides it, and then now I can use my modified collator. So when I run training with this modified collator, which adds zeros to the attention mask where there are padding tokens, now I can see the output of my Flash Attention debug composer callback. And now we can see in the attention layer, attention mask is not none, and it does have zeros. And the attention mask shape is 2048, but the attention mask sum is 201. So that means that there's only 201 non-padding tokens. The rest of them are padding tokens. And so the attention mask is 0 for those padding tokens. Also, the fact that the attention layer sees the attention mask is also because 0.0 is in the attention mask. And so the model's forward pass did return attention mask from the update causal mask method, and it did pass the actual attention mask to the decoder layer, which we can see here. And then eventually it finds its way to the attention module. Okay, so in summary so far, just to kind of do a quick reset, by default, using a Hugging Face model, LLM Foundry attention mask contains all ones for pre-training. When the attention mask contains all ones, the Llama model, Hugging Face's implementation, does not pass the attention mask forward to the rest of the decoder layer modules. It passes none. And so the attention mechanism never sees the attention mask, and therefore the Flash Attention forward, because it doesn't see attention mask, it never calls Flash Attention varlen func. And so all of that we can kind of confirm now based on this composer callback that we have built. Okay, so how do we know explicitly if Flash Attention varlen func is being used? Obviously, we can deduce that attention mask, if the attention mask is none, then it's not being used, and if the attention mask is not none, then it is being used. But it's always nice to visually confirm and actually look at what the result is. So to do that, in the LLM Foundry train.py, before the trainer is instantiated and before the trainer.fit method is called, I inject this code. So I import transformers.modeling Flash Attention utils, which is where Flash Attention forward and all the helper functions are defined. I save the original upad input, and then I save the original prepare FA2 from position IDs. Upad input is called if attention mask is not null. Prepare FA2 from position IDs is called if this if condition is true. And then I write myself a new UPad input where I'm going to inspect the inputs to UPad input, query, key, value, states, attention mask, query length. I'm then going to call the original UPad input and then inspect those outputs. And the reason I do that is because those outputs of UPad input eventually get passed on to Flash Attention varlen func. So I want to see, what is being passed to Flash Attention varlen func. And then I return the original UPad input with its correct inputs. And then I replace UPad input with my debug UPad input. So I'm monkey patching UPad input to inspect what's going on. So when I use my modified collator, my attention mask has zeros. Because my attention mask has zeros, Hugging Face LlamaModel passes it forward to the decoder layer and then the attention mechanism. The attention mechanism sees it, passes it to Flash Attention forward. Attention mask is not none, so UPad input gets called. And so this is what I see in my terminal, is I see all of my print statements that I added in my debug UPad input. And it's always exciting to see that because you're like, okay, this works. And it's always cool to kind of monkey patch things because you're altering the kind of built-in methods and inspecting things in real time. And we can see the inputs to UPad input, and then we can see the outputs. So some observations here. The query states that gets passed to UPad input has size 6, which is the number of items in the batch. So in this case, this was for a run with a batch size of 6. 2048 is the sequence length. 9 is the query number of heads, query heads, and 64 is the head dimension. Then query layer, which is one of the outputs of UPad input, now loses the batch and sequence length dimensions and instead has this total sequence length, which is the total number of non-padding tokens in my batch of 6. And that's 1,395. Number of heads is 9. Head dimension is 64. And then those sequences, we had 6 sequences. The first sequence has 220 non-padding tokens. The next one has 217. The next one has, let's see, I have it somewhere down here, 295. The next one has 183, 130, and 350. So the difference between each of these cumulative sequence lengths is the sequence length of each of those 6 batch items, non-padding tokens. And so if you add up the sequence lengths of the non-padding tokens of the 6 batch items, you get 1,395. To kind of double confirm this, I have this data inspector callback, which basically just looks at the batch and it counts the number of non-padding tokens and the number of padding tokens. And so I recommend running that, passing that callback as well so that you can manually inspect that, the first one was 220, the second one was 217, the next one was 295, so on and so forth. But this basically confirms that when attention mask has zeros, then Flash Attention varlen func eventually is called. So this was, a lot of work just to get to this point, but it was well worth it because now I know exactly what type of attention computation is taking place. So now that's done, I ran some training runs, and to my dismay, I found that Flash Attention varlen func utilizing runs were actually slower. So here's what that looks like. This is on a L4 GPU. The orange curve, loss curve, is my Flash Attention func, so the padded version, and the green one is my attention mask with zeros varlen func implementation. So the varlen version actually takes like 20% longer to run. And this was counterintuitive to me because the whole point of doing the varlen implementation was that it strips padding tokens, it's doing attention computation on fewer tokens, and that's, an optimization, so why is it not faster? Also looking at a A100, we see the same result. This red line is my flash attention varlen func run. This gray line is the regular batched flash attention func run, and that's even more than 20% in this case. My varlen is more than 20% slower. So this didn't make sense, and we were all kind of scratching our heads, and we discussed this with our research advisor, and we learned that this is likely because the Hugging Face implementation unpads and repads the batch for every layer for every forward pass. So if we look at flash attention forward, here we have attention mask is not none, and here we have flash attention varlen func, and we have this attention output unpad. Here it pads the input, and then that's the attention output that eventually is returned back to the rest of the model. So because of this unpad, flash attention, repad, process of unpadding and repadding every layer, every forward pass, this is why we're getting the slowdown of over 20%. And so the only solution to this is we have to implement our own custom model where it unpads the batch only once, and then at the end of training, it'll, repad it if necessary. So this is our next task. It's certainly a very large task. We've had a couple of folks in our group have already done a lot of work implementing the custom llama model. So this will be, you will see some videos from me on this. But again, closing thoughts, again, very interesting and surprising for me to see. And I see this again and again, that something that is a theoretical speed up based on the implementation may not be a practical speed up. And so this is something that I'm learning a lot as I do actual training runs. And this is why I recommend everyone to do actual training runs, because we can kind of see that on paper, the variable length kind of sequence packed flash attention function should be faster. But because of how it's implemented, not only is it not speeding up, but it's actually slowing down. So that's it for this video. This notebook I'm going to be publishing as a blog post, so I will link that in the video description below. Thank you so much for sticking around until the end, and I will see you next time.